Today, we're going to apply what we know about exponential functions and solve some real-world problems. You can use the date of June 10th. Your note packet should have 5 pages. These are the last 5 pages of notes. So in our previous lessons, we have learned that this is the correct exponential form, y equals a times b to the x power. We know that b represents our growth or decay factor. If the value of b is somewhere between 0 and 1, we know that we're going to have exponential decay. So the amount we have is declining. If the value of b is greater than 1, then we know we have exponential growth, and the amount we have should increase slowly at first and then rapidly. In the real world, we can use exponential functions to model real-world phenomena. So we use this type of function in science, in statistics. We use it for electricity. We actually use it for the finance world with credit card payments. So it does have many uses to model what's happening. So we're going to modify our original formula just a little bit to talk about percentage of increase or percentage of decrease at regular intervals. So if you're modeling growth, what we're going to start with is A, our initial amount. 1 represents 100% of what you started with, but we're going to add to that some percentage R, and then we're going to raise it to the power. If you're dealing with decay, we're going to start with our initial amount A. 100 represents what we started with, 100%, but we're going to subtract a percentage off. So if you think about this, 1 plus R is greater than 1. 1 minus R is between 0 and 1. So 1's representing growth and 1 represents decay. So R is going to represent our growth or decay rate. Typically, it's going to be provided as a percentage in the problem. We're going to convert it to a decimal when we sub it into our formula. X will be the number of time intervals that have passed that we're trying to calculate. So maybe we're looking at the growth of bacteria over 20 months, or maybe we're looking at the growth of money over the course of 15 years. So it'll be the number of intervals. In example 1, it says, if the population of a small town in Maine is 100 and grows by 6% per year, how large will the population be in 20 years? So we know that the population is growing. We're going to use a growth model. So we can see it's 100% of what we started with plus some percentage rate. A, our initial amount, is the population of 100. And the rate of growth is 6%, but we're going to convert it to a decimal. So we're moving the decimal 2 to the left for 0.06. And we're looking at the population after 20 years. So that's what our time interval represents. We're going to combine 1.06. And at this point, you can type this right into your iPad and let it generate an answer. We do want to round our answer according to the problem. So normal rounding rules tell me that I need to go up. So this will say we'll have about 321 people in that town of Maine after 20 years. In example number 2, we're starting with a bank account balance. We want to find it to the nearest dollar. We're starting with 100. We have an annual rate of 4%, so it's growing. And the money is left in the account for 12 years. So we don't touch it or withdraw any money. This is a growth model. We're going to sub in. We have 100 as our initial investment. 100%, which is the 1, will stay in the account. And then we're adding 4%. And we're going to do this for 12 years. So again, I'm going to simplify a little bit. And at this point, we're going to type it right into the iPad. We're going to round our dollar amount to the nearest whole dollar. So we'll have about $160 after 12 years. I think I would invest in something else. In example 3, it says in 1985, there were 285 cell phone subscribers in the small town of Centerville. The number of subscribers increased by 75% per year after 1985. How many cell phone subscribers were in Centerville in 1994? So again, we're modeling growth. We'll start with 285 cell phone users. Our rate of increase is 75%, 0.75. And 1985 is year 0. That means 1994 would be the 9th year. So I'm using a power of 9. And we'll put it together. Now, this is a correct answer based on the math because of the growth rate. But I think you have to think about the context of the problem. So even though this is a correct answer, if this is a small town, we might not have 43,000 people that live in that town. So while the growth rate is correct, at some point, the growth may level off, and maybe everyone in Centerville has a phone, but maybe there's only 1,000 people. So we want to be conscious of some of these strange answers. In example 4, we have radioactive decay is a typical example of an exponential function where the amount of material is reduced by 1/2 over a certain period of time, and they call this a half-life. Material M has a half-life of 100 years. There are 600 grams of material M. How much would remain radioactive after 200 years? So we know that this is a decay model, so I'm going to start with the 1 minus R. When you sub this in, our initial amount A is 600 grams. We're reducing the amount of material by half. But X, what value of X are you using? Is it 200 cycles? It's really not. If a half-life is 100 years, then 200 years represents 2 cycles. So our power is really to the second. So be careful that you don't fall for that dirty little trick. So we're subtracting off half of the amount. And after 2 cycles, we should have about 150 grams of material M. Let's solve this same problem, but change it for a 300-year cycle, which is really 3 cycles. So how much will be left after 300 years? Really, we're just changing the exponent, and we're down to 75 grams. If we solve it one more time and see how much is left after 500 years, everything is the same except for the power. So now the power is 5 cycles. And we're down to 18.75 grams of material M. The homework that you're going to do that goes with this assignment, both of them say growth and decay at the top. There's 2 pages, page 611 and page 612. You don't have to do the problems that I've crossed off, but you do have to do the remaining problems. In some of the questions, they're just asking you to write the formula, and then in the second part, they're asking you to solve the formula. Make sure you show me all work. If you want to do it on a separate sheet, that's fine as well. If you have any questions as you go through this assignment or this homework, please let me know. Have a great day.